Artificial intelligence is now writing your emails, summarizing your weekly reports, answering your search queries, and even helping you write code. We interact with these clean, friendly chat boxes every single day, often assuming there is a highly capable digital mind on the other side. But underneath that simple interface is a strictly structured mechanical system. What exactly is happening in the fractions of a second between the moment you hit send on a prompt and the moment a perfectly formed response appears on your screen? To answer that, we have to look inside a large language model, or LLM. A large language model is a type of artificial intelligence trained on massive amounts of text to recognize and reproduce patterns in human language. In this series, we will demystify the mechanics of these systems without relying on complex math. The modern AI experience is the result of a mechanical process governed by probability rather than biological thought. If you strip away the user interface and the branding, the core of a language model is a program designed to do exactly one thing: predict the next piece of text based on the text that came before it. That piece of text is called a token. A token is the fundamental building block of this prediction process, representing a single word or a fraction of a word that the computer can process. This chart shows how the model evaluates an incomplete sentence like, "The capital of France is." The system looks at those 5 words and assigns probabilities to thousands of possible next tokens. Paris gets a 99% probability, while London or banana sit near 0. The engine simply selects the highest probability token and delivers it to the user. At its most basic level, an LLM is a highly advanced autocomplete engine, guessing the correct response exactly 1 word at a time. The reason these systems can write poetry or code instead of just finishing a simple trivia sentence comes down to their scale. The large in large language model refers to the sheer volume of text the system absorbed during its training phase, often encompassing a massive fraction of the public internet. Processing all that text requires parameters. Parameters are the billions of adjustable mathematical dials inside the network that allow it to map out the intricate patterns of human grammar, historical facts, and common idioms. When you give the model a prompt, it enters the generation phase, formerly known as inference. Inference is the computational step where a trained model actively applies what it has learned to make predictions on new, unseen data. This diagram shows the complete inference loop in action. The model predicts a single token, appends it to your original prompt, and then calculates the entire new sequence to predict the very next token. This rapid, mathematically scaled guessing loop runs thousands of times a second to generate the responses we see on screen. Because this single prediction architecture maps so closely to how human language works, it is incredibly versatile. You can have the same model summarize a 50-page legal document, translate it into Hindi, and then write a Python script to email it, simply by changing the instruction at the start of your prompt. This versatility does not equate to comprehension. An LLM does not have awareness, beliefs, or experiences. It does not understand the world the way humans do. It is strictly optimizing probabilities. It strings together tokens that statistically belong next to each other, prioritizing the shape of a correct answer over its factual truth. This blind optimization leads directly to hallucinations. A hallucination is a phenomenon where the model confidently generates detailed information that is entirely false because it prioritizes statistical flow over factual accuracy. An LLM's priority is statistical coherence. Because it optimizes for the next likely word rather than for factual accuracy, the model functions as a sophisticated generator of text rather than a reliable database of facts. We've established that an LLM is a massive neural network trained to continuously predict the next token in a sequence of text. But that raises a critical mechanical question. How does plain English actually get broken down into the numbers and math required to make these predictions? Welcome to Knowledge Equity Partners. We are a multilingual channel dedicated to sharing practical knowledge to enhance your daily life. If you found this breakdown helpful, please subscribe, like, and share to stay updated on our daily videos and help spread valuable insights. Always keep your quest for knowledge high, and join us in the next episode as we dive into tokens, embeddings, and the hidden math of human language.